This video will contain solutions to exercises from section 6.2, and that is volume by either the disc or washer method. Now, the most important thing here is to start with a good sketch. You need a good, solid sketch so you can determine if you're going to integrate with respect to X or if you're going to integrate with respect to Y. So I'll start with number 7. 7 gives us the function y squared equals x and x equals 2y, and we want to rotate about the y-axis. So again, we want to start with a good, solid sketch. The bigger the sketch, the better it's going to be. Make sure on your paper that you're not trying to make some sketch about the size of a postage stamp. You need a sketch that's the size of a good homemade chocolate chip cookie. A sketch that's, got some size to it where you can label the parts and see each component of the sketch. So we have x equals y squared. That's a parabola. We know that's our sideways facing parabola. If you want to change this, of course, this is y equals the square root of x, but that's only the top half. So right now we have x equals y squared, which is a parabola that goes like this. We also have x equals 2y. Now, if we flip that, that's y equals 1/2 x. That's our line with the slope of a half and a y-intercept of 0. So that line goes from here, and it has a slope of a half. So it goes out like this. So we can erase this. This is going to be our closed region right here. And we're going to indicate that we're rotating around the y-axis by putting our rotation symbol on the y-axis. Now, before we rotate this, we want to find this point of intersection. So we can solve this, right? If we wanted to solve this, we would have y squared equals 2y. They're both equal to x. So that would give us, y squared equals 2y. And most of the time we can solve these in our head. We can ask ourselves, well, if I multiply something by 2, what can I multiply by 2 that's going to give me the same thing squared? Well, the only way you're going to get something squared equals something multiplied by 2 is if the number itself is 2, because then 2 squared is on this side and 2 squared is on this side, which means here the y value is going to be 2. So the x value is going to be 2 squared, or 4, or 2 times 2, 4. So that's our point of intersection, 4, 2. Now again, we're going to rotate this around the y-axis. So we're going to draw our reflection over here, right? We have this point here, and then we have our line and our parabola. So this is our reflection. Now, the instructions are very specific. They say find the volume of the solid, obtained by rotating the region bounded by the given curves about the specified line. Sketch the region. We've done that. the solid, okay, we have not done that. So what is the solid going to look like? Well, we're going to rotate this around the y-axis. So we're going to end up with a solid that looks like this. All right. We're going to have this cone-shaped solid, but the inside of our cone, if we want to think of it as a bowl, and that comes to a point, it wouldn't be a very useful bowl. It won't balance very well on a table. But the inside of our bowl is parabolic, right? The inside of our bowl is this parabola. So this is our solid. Then it says, sketch a typical disc or washer. Okay. So we're going to, we want a washer or a disc. So we have to ask ourselves, which way am I going to slice this to generate a washer or a disc? Well, if we were to slice this vertically, right, top function, bottom function, that would form something that would have height, right? It would have height over here. If I'm not going to draw my slice on my picture because I'm not going to use this. And then it would have another slice over here, our corresponding slice. And when we rotated this, we would not get a disc or a washer. We would get a cylinder from back in elementary school. That would be a cylinder. That's not a disc, nor is that a washer. And that's the method that we're going to learn in section 6.3, the method of cylindrical shells. We don't want a cylinder. So we want to visualize what would this look like if I sliced it vertically. And we're going to see that if we slice it vertically, we're going to get a cylindrical shell. So we don't want that. So what would it look like if we sliced it horizontally? Well, my corresponding slice would be here. We would end up with an inside that's empty. And then we would end up with our solid part. And that would give us our washer. Remember, we're looking for a disc or a washer. So we want to slice this horizontally, i.e., our typical slice, our typical rectangle, is perpendicular to the y-axis. That means we're going to integrate with respect to y. Okay, with respect to y. Now, what approach are we using? We're using washer, right? We're using washers. And we know that to do washers, our integral is going to be pi times the outer radius squared minus pi times the inner radius squared. And in this case, it's going to be dy. And then we're going to go from A to B. That's our method of washers. So our task here, pi outer radius, we're going to call that the outer area. I'm going to say I'm looking for the outer area in terms of y. Over here, I'm going to look for the inner area, and I'm going to put down in terms of y to remind myself that I'm integrating with respect to y. I have a lot of things written down in my problem right now that should remind me that I want to integrate with respect to y. First, I have a horizontal cross sectional slice. I have dy written down in my formula. I've written literally that I'm going to integrate with respect to y. I've indicated that my area is going to be a function of y, my outer area. My inner area is going to be a function of y. Now, we know these are circles, so that's going to be pi times the outer radius squared, and this is going to equal pi times the inner radius squared. And I'm going to write all these things down every time I do a problem to allow myself the highest probability of getting the problem correct. Now I have a bunch of templates written on the board. I have my formula written here for my volume. I have my formula written here for my outer area, pi r squared, area of the circle. I have my formula for my inner circle's area, pi r squared again. Now I'm going to now ask myself, what is the outer radius, right? What's the outer radius? Now, this is the point x, y, right? That's some arbitrary point on our curve. In this case, our curve is the line. So we can say, well, my outer radius, how far is it, right? My radius starts here, ends there. Well, that's x. And we can even put a little O on there and say that's our outer x. So that's going to be pi times my outer x squared, because the distance from 0 to this point horizontally, based on how we use the Cartesian plane, that distance is x. Now, I'm not done. I'm not finished. I want this function in terms of y. Right now, this function is in terms of x. So now I'm going to look at my given formulas, and I'm going to look at my sketch, and I'm going to say, okay, what is x in the context of this outer radius? Where is x? Well, x is on the line, and the line is x equals to y. So I can substitute in place of the x 2y, don't forget to square that, pi r squared, radius squared. And so here we have 4 pi, right? 2 squared is 4, y squared. So I found my outer area formula in terms of y. Now, our next task is to do the same kind of analysis, but do it in terms of the inner area. And again, this point, and it's kind of difficult to see, I'll write it up here. This point, we need to label this point. Well, this is an arbitrary point, so we can call this x. We could even say x sub I. It has the same y value because here we have a horizontal slice. So since we have a horizontal slice, the y values don't change, but we can put x sub I for inner x, right? Because we're really going to ask ourselves, how big is this radius? That's the radius of my interior circle. And that, of course, is x sub I. So this is going to be pi. I'll substitute x sub I for the interior x into my formula. Again, reminding myself, I want this in terms of y. I currently have it in terms of x. So I ask myself, where does this x live? What curve is this point located upon? Well, it's on the parabola. So on that parabola, x is equal to y squared. So this is going to be pi. I'll substitute in that value, which is y squared. Now, don't forget, that's my radius. Y squared is my radius, but we're squaring our radius. So we're going to get here pi times y to the 4th. Okay, now we've got our formula for our interior and our inner and our outer areas. And that's what we want to use to find our volume. So we're going to substitute those in. So our volume is going to be equal to the integral. Now we're integrating with respect to y. This point right here, of course, is the origin, 0, 0. So y is 0. Here y is 2. So we're going to integrate from 0 to 2. The pi we can factor out, right? There's a pi here and a pi here. We can factor that out if we want. My outer radius was 4y squared. So I'll put that here. Minus my inner radius. We said, remember, we factored out the pi. So we have y to the 4th dy. Now that's our volume. Now we can integrate this, right? This is just power rules. So we have pi. This is going to be 4y cubed over 3 minus y to the 5th over 5. And we're going to evaluate that between 0 and 2. It's always nice when one of your bounds is 0, of course, because when you plug 0 in here, you get 0. When you plug 0 in here, you get 0. All right, I'm not going to do the arithmetic because I want to have time on this video to do as many examples as possible. You all can plug a 2 in here and get 32 over 3, and plug a 2 in here and get 32 over 5, and then get a common denominator. And well, let me show you a trick since it came up while we were doing this problem. Here's pi, all right? Here's pi. If you plug a 2 in here, 2 cubed is 8, 8 times 4 is 32. That's over 3. If you plug a 2 in here, 2 to the 5th is also 32. And so that's 32 over 5. Now, here's a trick from arithmetic that maybe you've seen, maybe you haven't seen, but it really makes things easy. Here's our pi, our common denominator here is 15, right? 15, 3 and 5. So 3 goes into 15 5 times. So here you have 5 times 32. Don't multiply that out. This is when you have the same numerator here, you can do this every time. Now, what do we have here? 5 goes into 15 3 times, so we have 3 times 32. Well, you have 5 32s, take away 3 32s. I mean, in essence, you have 5a minus 3a. 32 happens to be your a. We all know from algebra that's 2a. So this is going to be pi. This is going to be 2 times 32 all over 15, or 64 pi over 15. So when you have the same value in the numerator of two fractions, there's no reason to multiply this out and make these numbers big and then have to work with big numbers. You can just use this trick. Okay. All right. So that's number 7. I'll turn off the video and come back to you after I've got the whiteboard erased. Okay. The next question I'll work on is problem 16. 16 is x equals y squared, x equals 1. And they want us to go about the line x equals 1. Okay, so we're not going about an axis here. We're going to go about the line. Again, we want to start with a solid sketch, right? A solid sketch. So what do we have for our functions here? We have x equals y squared. That's parabola goes this way. And we have the line x equals 1. X equals 1, of course, goes like this. Now we know where this intersects, right? This is the point 1, 1. Wow, that's not a very good one, is it? And this here is the point 1, negative 1. Now they want us to spin this, right? They want us to rotate this about the line x equals 1. The line x equals 1 is right here. So that's our axis of rotation. Our corresponding piece, right, when we spin this around, our corresponding piece is going to be this parabola right here. Now, we've got our sketch, and we have to ask ourselves, which way am I going to make my representative slice? Where is my typical rectangle going to be constructed? Again, if we were to put our rectangle vertically and then swing this around 360 degrees, we're not going to make a washer and we're not going to make a disc. We're going to make another cylinder. So again, in this problem, we're going to need our slice to be horizontal. And then when we rotate that around the line, remember we're rotating around x equals 1. When we rotate that, we don't get a washer, right? There's no hole in the middle. This is going to be a disc, right? We're going to use a disc here. This just forms a solid disc. Now, once again, we're integrating with respect to y, right? We have a horizontal typical rectangle. which implies that we're going to integrate with respect to y. Now we're using disks here. So the volume using disk is the integral from a to b. And we're going to have just pi r squared. And we're going to have dy. We don't need to write r sub I or r sub o here because we don't have an outer or an inner radius. We just have a disk. It just has one radius. So that's our formula for the volume. Now, once again, we're going to have to find the area function, right? Pi r squared is our area function. Now, our area function here, because it's horizontal, we're going to integrate with respect to y. So I'm going to write a y here. My area is going to be pi r squared. I don't need an r sub o or an r sub I because I just have one radius. When I get disks, just one radius. I don't have a hole in the middle of this. It's not a washer. Again, all the things on the whiteboard that remind me that I'm going to integrate with respect to y. I have a horizontal cross-sectional slice drawn on my sketch. I've written down that I'm going to integrate with respect to y. I've written my integral, my typical integral, and my definition integral with a dy. And I've told myself my area function is going to be in with respect to y. It's a function of y. Now, our job at this point, right, is to find our radius. That's our job. So we look at this and we say, okay, well, the radius is right here, right? Here's the radius. That's all. Well, it's not touching an axis, so it makes it a little more complicated to find the radius. It doesn't make it complicated. It just makes it a little more complicated. Again, we start doing the same things that we've done so far. We tell ourselves that's the point xy. And then we draw what I like to call the 3-bracket method, okay? We've got our bracket for the radius. Here, this bracket is x, right? From here to here, that would be x. That's how a Cartesian plane works. And then our third bracket goes from our axis to our axis of rotation. Our third bracket is going to be this bracket right here. And we ask ourselves, how big is this bracket? Well, this is the line x equals 1. So that bracket is 1. These 3 brackets, whenever you're rotating around a line, it's not one of the axes. These 3 brackets will always help you find the radius. One of your brackets goes from the axis parallel to your axis of rotation to your axis of rotation. And then the other 2 brackets go from your point xy to your axis of rotation and from your point xy over to your axis. If you draw those 3 brackets, you'll always be able to find your radius. See, look at what we know. We know this little bracket plus this bracket, x plus r, is equal to this big bracket, that's 1. Well, from there, I can see that my radius, solving for r, my radius is 1 minus x. So I can come over here and I can plug that in, pi 1 minus x squared, because my radius is 1 minus x using my brackets. Now, before I square that, I'm going to remind myself, I don't want an x. I want a function of y. But I know what x is. This xy, this point lies on the parabola, and on that parabola, x is equal to y squared. So I can replace this x with my y squared. And I get pi, I get 1 minus y squared. And let's don't forget, we're taking the radius squared, area of a circle, pi r squared. So we're going to square that. Now we're going to go ahead and multiply that out. That's 1 minus 2y squared plus y to the 4th. There is my formula for the area in terms of y. Now I can come back over here to my integral. Now I'm integrating with respect to y. So I start here and I go to here, right? That's the bottom and the top. So this is going to be an integral. It's going to go from -1 to 1. I have pi r squared is what I need. I've got pi r squared right here. I figured that out. I'm going to go ahead and put my pi out in front. and I'm going to have 1 minus 2y squared plus y to the fourth dy. Now, this is one of those instances where symmetry is going to pose not a problem, but it's going to give us an assist, right? Symmetry is going to give us assists. If we look at this figure, the portion in the first quadrant and the portion in the fourth quadrant are exactly the same size, right? There's symmetry between the first quadrant and the fourth quadrant due to the fact that we have an even function in y. It's not really a function, but it's a function in y, if you want to let me just kind of say that without it being perfectly mathematically correct. So what are we going to do about that? Well, since we have the symmetry, we know that the volume down here and the volume up here, they're equal. So I'm going to rewrite this. I'm just going to find the volume of the top half. So I'm going to multiply by 2 to represent the fact that I'm only doing half of it. So there's 2 pi. And now I can go from 0 to 1, right? Because the top half starts at 0, goes to 1. And I can have 1 minus 2y squared plus y to the fourth dy. Greatly simplifying my work, because instead of having to integrate from -1 to 1, plugging in a 1 for my fundamental theorem of calculus for f of b, plugging in a -1 for my fundamental theorem of calculus f of a, I can now plug in a 1 and a 0 and just multiply by 2. So when we integrate this, we get 2 pi. The integral of 1 is going to be y. This is going to be minus 2y cubed over 3. And this is going to be plus y to the fifth over 5. And we're going to evaluate that between 0 and 1. Okay. And now when we plug in 1, we're going to get 2 pi. This is going to be 1 minus 2/3 plus 1/5 minus, when we plug in 0, that's going to be 0, that's going to be 0, and that's going to be 0. So we don't need to do that part. So we have 2 pi. Our common denominator here is again going to be 15. 1 gives us 15 over 15. 3 gives us 3 goes into 15 5 times. 5 times 2 is 10. 5 goes into 15 3 times. 3 times 1 is 3. And so we get 15, take away 10, 5 plus 3, that's 8 times 2. So we're going to get 16 pi over 15. And assuming I didn't make a silly arithmetic mistake, which is a big assumption, that's the answer to number 16. Again, I'll pause and be right back with you after I erase. All right, the last problem I'll work on will be number 25. I'll do part A. In question 25, they give us an integral. They have the integral. This is part A. They have pi times the integral from 0 to pi over 2, 0 to pi over 2 of cosine squared x dx. And it says in the instructions, this integral represents the volume of a solid. Describe the solid, right? Describe the solid. So where we have to go from here is we have to think about the fact that the volume is equal to, now there's not two functions subtracted here, so it looks like this is a disk instead of a washer, right? Because a washer would be pi outer radius squared minus pi inner radius squared. We only have one function here. So it looks like this may be a disk. So our bounds would be a to b, and we would have pi times r squared dx, right? That's our formula for the volume if we're using the method of disks. So it looks like here our radius, right, r squared cosine squared, our radius is cosine x. That's what it appears from looking at the problem right now. Our radius is cosine. So if we draw the cosine curve, right? The cosine curve goes like this. And we're integrating between this is an x dx, so this is a value of x. This is x equals 0, and that's x equals pi over 2. Well, x equals 0 is here, right? And this is pi over 2. If we're drawing our graph of our cosine function, that's the point pi over 2. So they expect us to use our intuition and our problem-solving skills to just, there's no set of steps, is what I'm trying to say here. They're just expecting you to think this through. Our bounds are 0 to pi over 2. So that means we're only talking about this much of the cosine curve, right? This much here. And our radius, right? Our radius, if we draw our typical rectangle, our radius this is x, y. We need our radius to be cosine of x, which means we need our radius to be right here. That's r, and that radius is y, right? That's the point x, y. So our radius, we need it in terms of x. We'll write it like this. But right now, our radius, looking at our picture, is y, because that's how the Cartesian plane works. The distance from here to here on the Cartesian plane is going to be y. And again, we're just working backwards here. We're using our intuition and our experience and our problem-solving skills and trying to put together ideas. If the ideas we put together turn out to be wrong, we'll just start with different ideas, new ideas. So would it be the case then that if this is my radius is y, what does y equal? Well, our function we draw is cosine x, right? That's our function. So y does equal cosine of x, and that fits into our formula then, because when we take our area formula in terms of x, area is going to be pi times our radius squared, and we've decided that our radius is cosine, so that's going to be pi times cosine squared of x. So that fits with our problem. So we're rotating this portion of cosine about the y-axis, right? That's the portion of the cosine curve between 0 and 2 pi rotated around the y-axis. So if they asked us to draw, right, draw this solid, our solid would come down here. It would have its corresponding piece over here, and then it would look like this, where this is the graph y equals cosine of x, and this is the point pi over 2, and of course this is the point 1, right? Because that's the top of the cosine curve. All right, that completes my video on section 6.2. I know some of you probably tuned in looking for problems 39, 40, and 41. I'll discuss those when we get together in class on Tuesday, and maybe I'll do a video also just for those problems by themselves, but it'll come after we go to class on Tuesday. So if you happen to turn in your homework and you have not addressed problems 39, 40, and 41 in your homework, don't worry about that. That's not that big a deal. I'll still give you full credit for your homework assignment. All right, thank you very much.